guys, nice to see you. How are you doing? Tired? Okay, so let us make one more step before we can. So let us recall what we did last time and discuss. So we introduced a new concept of kinetic energy, potential energy, and internal energy. So we started from introducing this kinetic energy work relationship when if the system changes only by change of velocity, then work done by external force on the system results only in change of kinetic energy of the system. Obviously, that's not always the case, and sometimes system can change without it can change its state without changing its velocity. So initial and final velocity can be the same, let's say equal to zero. However, we consider this example with a block which is lifted over horizon. So we go from zero, like ground state, to some excited state, and then we increase potential energy. So we also introduce this concept of potential energy and claim that there is a conservation of energy, so sum of kinetic and potential energy remains constant. So that is true when we don't have any dissipation of energy in form of like friction force performing some work, which is so-called non-conservative force. And if there is some friction, then because of the contact between two surfaces, they warm up, so the internal energy temperature increases, internal energy increases, and part of kinetic energy is transformed into the heat. Means it goes from, there's a transformation from kinetic energy to internal energy. Taking this into account, we consider that the sum of kinetic potential and internal energy should be equal to constant, means that it doesn't change. The sum of all these energies do not change when we go from one state of the system to another. So now we will continue our discussion on these topics based mostly on application of conservation of energy. There will be one interesting example we will consider. But before that, I think that we had a quite interesting example for drag force application with this boat on water, which slows down because of drag force. I think it makes sense to have some application case of friction force because we didn't consider it in more details. So let us first consider some application of friction force and then conservation of energy. So now we will deal with such a system. We have x and y axis of coordinate. We have two blocks. Big one and small one. So let's denote mass of the big block with capital M and small block with small m. Now we will consider only this interface between two blocks as interface where we have some kinetic friction. So kinetic friction, as you remember, is characterized by kinetic friction coefficient mu k. So we have this information, we have mass. Then we consider some wheel here at the hinge and a wire which connects both masses. So this wire, assume that it doesn't possess any mass and it's not stretchable. At the bottom here, below the big box, we have some supporting surface which does not provide any friction. So it's frictionless surface. It slides without friction on the surface of this supporting plane. So this is our x, this is our y. Now the question we would like to answer, what force F we need to apply to bottom big blocks in order to move it with constant acceleration A. It's constant. So let's see what forces are acting on these boxes. So let's first consider the small box. Let's say that it's body number 1. So we have mg, weight of the box. We have reaction of the surface, which is surface of the big box, and 1, let's call it. Then we have tension in this row. It will be T1. And since this body will slide, top box will slide with respect to the bottoms, and bottom one moves to the right, the top one moves to the left. So in this case, the friction force, kinetic friction force, will be aligned in opposite direction to its motion. So it will go to the right. It will be Fk, kinetic friction 1, let's call it. And this will be acceleration. So acceleration is in the opposite direction to axis x for top box. Now let us draw also forces which are exerted on the bottom box. And let's do it separately because our figure will be overcrowded. So this is the big one, M capital. So we have weight, but here we have sum of two boxes. It will be capital M plus small m times G. We also have reaction of this frictionless surface that will be N2. We have tension, we can show it here also. This is tension here. Let maybe show this tension with different colors so we can see it better. So here we have tension and here we have tension. So this is T2. So this tension T2. And if friction force exerted on top box is aligned in direction of axis x, then the same friction force which exerted on bottom block should be in opposite direction according to the third law of motion. So we have also Fk2. So these are the forces which are exerted on both boxes. Now what we need to do, we need to write equations for x and y axis directions for both boxes. Let's start from box number 1, the small one. So what do we have along axis x? We have minus m times a, minus because this acceleration is in opposite direction to axis x for small box. That will be equal to minus T1 and plus Fk1. For axis y, we get 0 because we don't have any acceleration along axis y. That will be equal to n1 minus small m times g. So that's for block number 1. And the same let us write for block number 2 with larger mass, capital M. So for axis x, we have capital M times A, because now we consider this block separately. Keep in mind, it's not capital M plus small m, because this block is moving to the right and this block is moving to the left. So they are not moving as the same block. So that is important moment here. So we have m times a, which is positive because it goes along axis x. Then it will be equal to minus T2 minus FK2. And here we forgot to draw the driving force F, which we need to find. That will be plus F in order to move our blocks with constant acceleration A. And for axis Y, we get the following. It will be also 0 equal to n2 minus m plus small m times g. Okay, now before we proceed further, we need to highlight two things here. First of all, T1 is equal to T2 because this is not stretchable uh, wire, and also the magnitude of kinetic friction Fk1 is equal to the magnitude of kinetic friction Fk2. So we just take into account the sign of this friction in order to define in which direction it will be. But in terms of magnitude, we can substitute them by Fk, kinetic friction force, because by magnitude they are, according to third law of motion, they are equal to each other. So now let us pick up equation for x direction for small box and for large box. Let's write it down separately. So it will be minus m times a equal to minus t. So now instead of t1, we write just t. So it's equal to t. Then plus, instead of fk1, we write fk. And second equation, it will be capital M times A equal to minus T minus Fk and plus F. So now what we can do here, let us subtract first equation from the second one. So what we get then, it will be capital M plus small m times acceleration A equal T will cancel out. So here we will have minus, well, let's write F minus 2Fk. Okay, can you tell me what Fk will be equal to? Kinetic friction force we gave several lectures ago. Mu k times n1, which is, let's say, if it's here, so this is the surface which possess some friction, and this is reaction of the surface n1. So n1 will be equal from this equation, n1 is equal to mg, and that's why for friction force, kinetic friction force, we know the kinetic friction coefficient. We can write that this will be equal to mu k times mg. So now let us substitute this here, and we will have capital M plus small m times A is equal to applied force minus 2 times mu k times mg. And from here, we extract our force F we wanted to know, which is equal to capital M plus small m times acceleration A plus 2 mu k times mg. So this is the answer to our question. So once we finish with this application of friction force, let us go closer to our current topic, which is conservation of energy. So this is the system which we are going to consider. This is some ground surface. And on top of this, we have some ramp. With the edge of this ramp at the height, which is horizontal, you see it's horizontal, and the height is h. So let us assume that we have some mass, some block with mass m, and it moves with some initial velocity v naught to the right along, let's consider along axis x. So it slides without any friction on top of this ramp and reaches the edge and then falls down and flies certain distance from the edge of the ramp s along axis x. So first question we want to answer, what will be this distance s? So what do we have here? We have initial velocity, we have height of the edge of the ramp, which surface here is horizontal at the edge, and we want to find this distance s. Any suggestions what we need to determine here? Right, we need to know velocity at this moment at the edge of the ramp. So let's show it here. Oh, okay. This is v in this moment of time when it drops, and another parameter, time. Yeah, we need to know time. It takes for the block to fall down from this edge of the ramp to the ground level. So let us first determine the velocity. So how do we approach it? We know that surface like friction is negligible, so we can write that K1 kinetic energy at the first state plus potential energy at the first state is equal to K2 plus U2. What it means? M times V square, V naught square divided by 2, that is our initial kinetic energy. So what about potential energy? It's 0 because it starts from the 0 level. So 0. That will be equal to m times v square over 2 plus, now we already have some potential energy, that will be mgh. So mass can be cancelled out, and we can write that v naught square is equal to v square plus 2 times gh. From here, we get expression for velocity at the moment when our block will fall from the ramp. So that is square root of v naught square minus 2gh. Okay, so first parameter we determine. So how we determine the time it will travel? Okay, so from where you took this equation? We derived kinematic equation for the motion along a straight line with constant acceleration. So here what initial velocity in y direction is 0, so we don't consider initial velocity. So the component which results from the displacement which results from constant acceleration is equal to a times t squared divided by 2. And um, in this case, a stands, we replace with g because we have free fall acceleration. So that's why we can write that h is equal to g times t squared divided by 2. And from here, we get t is equal to 2h divided by g under square root, which actually write what you said at the beginning. So now we have time, and very simple step and straightforward. Since we have horizontal orientation of this velocity vector, we need to just multiply velocity by time, and that will give us s. So s will be equal to v times time. That is equal to square root of v naught square minus 2gh, and times square root 2h over g. So that will be equal, we put it under the same square root, 2h over g times v naught square minus 2gh. So this is the answer to our question, what will be the distance s. Now let us go to second question. First of all, what will be the height h, let's call it h prime, when s will reach its maximum value, that will be x maximum, and what it will be equal to. So let's take a look on this figure, and any suggestions what should be height in order to reach maximum zero? Zero? Well, we need, it cannot be equal to zero, so we need some ramp. So the, if we set h to 0, there is no ramp, it will be just a surface. So it can go from very small to very large. So any suggestions where, in which direction we should go? Larger direction. Huh? To the larger direction. To larger, okay. Good point. More time, more distance, that's true. But if we go to larger height, the velocity will very small, or at some point it will not even come to the top. So the velocity will be very small and time will be large, but product maximum. So if we go for very low ramp, then velocity will be high, but time will be very short. So there is a problem. So we need to find some compromise. And that's a classical example when we have some dependence with maximum. So somewhere in between, somewhere at the compromise value of the height of this ramp, this S will reach its maximum value. So any suggestions how we approach this problem? Like this question? Um, yes, yes. So that is general from 0 to plus infinity. Well, let us discuss a bit more in details. We'll make it clear for everyone. So if there is some function, let's say y is a function of x, and that function gives us, so we can delete this, don't need it now. That function gives us the following plot. So this is x, independent variable. This is our function value y. And it goes up and then down. So that's a function with maximum. So here somewhere we have maximum. And this is x prime value at which our function f gives maximum value. So now, if we take first derivative in this region of the function, so df over dx will be larger than 0. So y is larger than 0 because this is x1, this is x2. When we go from x1 to x2, function increases. So second value of function is larger than first value of function, means the difference will be, the derivative will be positive. So if we go in this region and take derivative, then this will be negative because function decays. However, if we go for region next to the maximum, function doesn't change. We slightly change the x, but function doesn't change. And that means that df over dx will be equal to 0. So that's why if we have some function and we want to know the value of independent variable at which this function gives us the maximum value, then what we need to do, we take first derivative of this function over independent variable, set it to 0, and solve it for independent variable which satisfies this condition. And that will give us this x prime. So now we have some real case. We have distance our block is traveling as a function of h. So where is our solution? This is our solution. Let us rewrite it a little bit. So let's write it here. S is equal, well, we can write it already as a function of h is equal to square root 2h over g times v naught square minus 2gh. And this is equal, let's open this parenthesis, will be 2h v naught square over g minus 4g times h square over g. G and g we cancel out. Also, we can take out from this square root this 4. So it will be 2 square root of h times v naught square over 2g minus h square. So this is in just rewrite a bit in different form, so it's easier for us to take derivative. This function of s versus height. Now, what we need to do, we need to take first derivative of this function over ds over dh and set it to 0. So what will be our first derivative? So 2 we can keep here as constant. Then derivative of this square root will give us 2 times square root h v naught square divided by 2g minus h square. And now we need to multiply it by the argument of the square root, like derivative of the argument of square root. So it will be v naught square divided by 2g minus 2h. So we are done with the function. Now we set it to some special condition which we need, and that is equal to 0. So let us determine when this first derivative will be equal to 0. So here it's nice because we even don't need to look at the denominator. We look only at numerator. So this parenthesis should be equal to 0 in order to get all this expression equal to 0. So from here, we write that v naught square over 2g is equal to 2h. Well, we can put here h prime already because it's not just some random h, it's h which satisfies these conditions for first derivative to be equal to 0, means at h prime we get maximum value of function s versus h. So from here we can express that h prime, this value of the height when we get maximum distance of traveling of this box, which was sliding on the ramp, will be equal to v naught square divided by 4g. So that is actually answer to our first part of second question. Then we also wanted to know what will be actually this distance. So how we address that one? We need to substitute this h prime into the expression for s. So we substitute it here. So let us do it. S maximum will be equal to 2 times square root h, we have v naught square over 2g times h, and instead of h we put v naught square over 4g minus h square. So that will be v naught force power over 16 times g square. So we have 2 times square root. Here is v naught in the force power of 8 times g, and minus v naught force power 16 over 16 times g squared. So eventually we get 2 times v naught square over 4g. Sorry, here is g squared because we have g here and g here. And we cancel out this. So our answer for maximum distance, it will travel v naught squared divided by 2g. So keep in mind this answer for h prime. and for S maximum. This is S maximum. So this is the general solution. And if you have question like this, if you have some function with versus in like as function of independent variable, and you ask at which value of independent variable your function will reach the maximum, that is the way to go. You take first derivative, set it to 0, and solve for this unknown independent variable. Now, let us take a look at this equation for s as a function of h. Let's write it down separately. S is equal to 2 times square root. What do we have here? H times v naught square. H times v naught square over 2g minus h square. 2g minus h square. Actually, in this specific case, it is possible to answer second question in a way straightforward and way more elegant way than taking derivative. That is general solution, but this particular case has a special, very nice and simple solution. Any ideas what we can do here? So keep in mind what is the question. It's h prime when s is equal to s maximum. If you probably look very long on this equation, you will see eventually, but it's not so easy to see. So let me. Oh? When what is 0? Velocity is 0. Well, yeah, but then you get completely unrealistic solution because you get negative value under square root, you get imaginary solutions to this equation. So if you see something like this, it kind of could be considered as an option. But if you have some imaginary solution, means for a real case, then you start to understand that something is wrong. So this solution has some limits. It cannot cannot be equal to 0 because it will not go to the parameter, and there's nothing will happen. So it's by definition not possible. And this imaginary like negative value at under square root kind of a signal to this. So what we need to do here, we need to rewrite this. Yeah. To achieve this maximum, we need the equation under the roots to be maximized. Yes, exactly. It's like a function of h squared, so it's a parabola, and if this upside down parabola, so it has its maximum. Yeah, which we can find. Yeah, so we found it by taking first derivative. So that is this original first version, how we solved it. So it's classical approach, and that works. It just the thing is that for this particular case, there is an option to do it without derivatives. Let's see what we can write here. So let's see. I will even change the color so you see that it's not part of the. Okay, yeah, can be considered. Let's see here in this. These formulas into energy. For example, the first one looks like a kinetic, the second one. Well, we did that when we had to calculate the velocity. Yeah, so We already have it here. It's integrated into this equation. S is equal to 2 times square root. So what will be if we have h minus v naught square over 2, no, not 2, but 4g. 4g in second power. Let's open this parenthesis. So we will have h square minus 2 times v naught square over 4g times h, yes, and plus v naught square over 4g in second power. So look at this part and this part. They are actually the same, only difference is the sign. So here we have 2. So we can rewrite this equation as like modified. Let us do it. We just have this additional term here, which we don't have in our equation. But we can take it into account because we will, first of all, we will use it with different sign in order to match sign in our equation. And second, we will just add this term v naught square over 2g, 4g in second power in order to have everything the same. So we can write here that this equation will be equal to 2 times square root. First, we need to add this v naught square over 4g in second power. And then we subtract this guy. So it will be h minus v naught square over 4g in second power. So this is equal to this. But now, since we modify this equation in a convenient form, we can immediately answer the question. If we want to know at which height of the ramp the S will be maximum, it tells us that at that condition, when we don't subtract anything from this term. So this will be the maximum, because if we subtract something, that will already result in smaller than maximum. So this means that this, for maximum S, this term should be in the parentheses here, should be equal to 0. Means that H should be equal to V naught square over 4G. And if we check this solution with our previous solution, we get the same answer. Now again, if we substitute this into this h into this equation for s, we will get the maximum value for maximum distance. So this is true only for this specific case. That's just nice example. But of course, in general case, you will go for first derivative and find the maximum condition. Okay, with this, we finish our consideration of applications, conservation of energy and friction force. Thank you very much for attention. Have a good weekend and see you on Monday. We will continue our course. Take care.